The next moment is moment due to the uniform soil reaction at Hill. So this is when we prolong here, we obtain the uniform. This is uniform, this is varying pressure. So is determines the moment due to uniform soil reaction at Hill. Let's say this is moment 3. This is uniform reaction and this is triangular. So our aim is to determine the moment at this uniform. This uniform. Now at here. So to obtain this moment is obtained by taking moment 3. The pressure of wheel times perpendicular distance. So it will be equal to the pressure of soil at base, which is 91 times the width of hill 2.9 times 2.9 divided by 2. So it will be equal to 91 times 2.9 times 2.9 divided by 2. It will be equal to 382.66. This is kilonewton meter per meter. The next is moment due to triangular. This one due to triangular. Moment due to triangular. This triangular this is when we prolong here, this is pressure 2 and this is pressure 3. Now let's determine the pressure difference from this point, from pressure 2 up to pressure 3. This one is obtained by taking pressure 3 minus pressure 2, and this is the height of this triangular, which is the width of hill slab, which is 2.9. So moment due to triangular pressure. Let's say this is moment 4. This triangle is in this nature. So this is pressure 2, pressure 3, and this is the height, which is 2.9, and this is horizontal force. Let's say this force, horizontal force, and this is pressure. This pressure is obtained by taking pressure 3 minus pressure 2, which is pressure 3 is this one. Pressure 3 is 142.8 minus pressure 2, which is 21. It will be equal to 142.8 minus 91. It will be equal to 51.8 kilonewton per meter square. Now, horizontal force will be equal to this pressure times, because it is triangular, so it will be equal to a half times horizontal force, which is pressure times h, which is times h. So it will be equal to a half point times 51.8 times h, which is 2.9. It will be equal to times 0.5 times 2.9. It will be equal to 75.11. 75.11. Now, after that, we determine the maximum moment for this triangular pressure. So maximum moment, let's say this is moment 4. It will be equal to this horizontal force times perpendicular distance. This perpendicular distance is h divided by 3. So times h divided by 3, h times h divided by 3. So it will be equal to this 75.11 times h, which is 2.9 divided by 3. It will be equal to times 2.9 divided by 3. it will be equal to 72.61. This is kilonewton meter per meter. Now, let's determine the design moment at point C. The design moment at point C. The design moment at point C. The design moment at this point. This rotates about, so it will be clockwise direction. So we plus. So moment at point C, it will be equal to moment 1, moment due to uniform soil reaction, moment it uses soil reaction plus also this way to the base rotates about C, so also rotates in clockwise direction. We plus moment 2, moment due to moment for base at hill slab, and the next is moment due to the uniform soil reaction. Uniform soil reaction rotates in this way. This is uniform reaction. So because it is downward, so it acts, it rotates in this way. It rotates in clockwise direction to this point. So we minus by moment 3, moment due to the uniform soil reaction. Also, we minus by moment due to this triangular pressure reaction. Minus by moment 4. So moment C, it will be equal to moment 1 was 559.27 plus moment 2, which is 56.52 minus moment 3, which is 382.66 minus 72.61. Therefore, moment C, it will be equal to 559.27 plus 56.52 minus 382.66 minus 72.61. It will be design moment, which is the maximum moment for that will be used for designing. 160.52. This is kilonewton meter per meter. After obtaining this, the maximum design moment at point C. Now let's determine the reinforcement for the hill slab. Area of reinforcement is obtained by taking design moment at C over 0.7 FYZ, but effective depth is obtained by taking thickness of stem minus curve of the base minus main diameter divided by 2. Effective depth, thickness of this was 500 minus curve of the base was this one. Curve of the base was this one, was 50 millimeter. So we minus by 50 minus 20 divided by 2. It will be equal to 500 minus 50 minus 10. It will be equal to 340. This is millimeter. Effective depth 350. This is millimeter. Now, after that, we determine the value of K. K is obtained by taking design moment at C, FCU, BD square. So it will be equal to 160.52 x 0.6 over FCU, which is 35 times breadth, which is 1000 times 346 square. So the value of K will be equal to 16.52 x 0.6 divided by 35 times 1000 times 340 square. It will be equal to 0.03967. So the value of Z will be equal to effective depth 0.5 plus 0.25 minus K over 0.9. Should be less than 0.95 effective depth. So when we divide by this one, 0.25 minus under root plus 0.5. We get here the value of Z is 0.95 times effective depth. So the value of z is it will be equal to 0.95 times effective depth, which is 340. The value of z it will be equal to 0.95 times 340. It will be equal to 323. This is millimeter. This is the value of z. After that, we substitute into this formula so as to obtain the value, the area of reinforcement for hill slab. So it will be equal to 160.25 exponent 6 divided by 0.87 Fy, which is 500 times the value of z, which is 323. The area of reinforcement will be equal to 160.6 divided by 0.75 times 500 times 2 times 3 to 3. It will be equal to 1152 millimeter square per meter. This is the area provided for the hill slab. Now, how to determine the area required? The area required for the hill slab. The area required we find from the table the maximum is the maximum closer to this area. For the diameter of 20, the maximum, our area is this one. Our area is 1152. The maximum closer to this area is this one. So is this one at the diameter of 20. So we say provides this hill slab provides H with diameter of 10. This is high reinforcement at a spacing of 20 millimeters center to center. Provides a tension of 20 millimeters at a spacing of 200 millimeters center to center, which gives the area of 1570 millimeters square per meter. This provided at near face of the at the top of the retaining wall. At the top. This hill slab provides provides the soil pressure which acts downward, so it provides the tension at the top. Provides the tension at the top of this hill slab. So at top face. The next is design of reinforcement for toy slab. Reinforcement for toy slab. This toy slab acts as cantilever, which is fixed at steam. Acts as a cantilever. This is toy. Now this is toy. Acts as a cantilever. This is cantilever, which is fixed at steam with upward soil reaction. Acts as a cantilever which is fixed at steam with uniform upward soil pressure. This one here with downward soil pressure, but for this case is upward soil pressure at toy slab. So to obtain the design moment, because it is fixed, so the maximum pressure acts at point B, the maximum pressure. So in order to determine the design moment, we find the maximum design moment at fixed point, which is at point B. Now let's find the maximum moment, design moment at point. Let's find design moment at point B. Design moment at point B. Design moment at point B is obtained by taking the moment due to the soil reaction moment due to upward soil reaction at toy, at toy. The moment due at toy, at toy. But the pressure. For this case, the pressure, which is the pressure of toy, which is pressure 1, was 162.4 kilonewton per meter square, is assumed is assumed is assumed to be uniform is assumed to be uniform over the whole width over the whole width over the whole width of the toy. Now, to determine the design moment, the moment due to the soil reaction, we take design moment. Let's say this is moment 1. So we take moment 1 to be equal to soil pressure at toy, because it's assumed to be uniform over the whole width. So we take this soil pressure times perpendicular distance. So 162.4 times the width of this toy is 0.7. We multiply by, so as to be getting kilonewton, and its perpendicular distance 0.7 divided by 2. So 0.7 times 0.7 divided by 2. It will be equal to 162.4 times 0.7 times 0.7 divided by 2. It will be equal to 39.7 kilonewton per meter. The next is to determine the moment of base at toy. So during the design of toy slab, there are two only moment due to the upward soil reaction at toy, and the moment of base at toy. Let's say this is moment 2. So this moment is obtained by taking moment of base, which is weight of base. This weight of base was 38.4 times its perpendicular distance. So in order to obtain in kilonewton per meter, because this is uniform distributed load, we multiply by total width of the toy, which is 0.7 times perpendicular distance, 0.4. After that, we get the maximum moment. So to obtain the design moment, we multiply by factor of safety. So factor of safety 1.4 times 38.4 times the width of toy, which is 0.7 times 0.7 over 2 perpendicular distance. Because this toy act on the whole width of the base, so we divide it by total width of the base. So the answer will be equal to 1.4 times 38.4 times 0.7 times 0.7 divided by 2 divided by 4. It will be equal to 0.29. This is kilonewton per meter. Now, let's determine the maximum moment at base. Maximum moment at base. How can we determine the maximum moment at base? Because for the design of toy, we have two only moments due to the upward soil reaction. So because we are designing moment about B at point B, so moment due to upward soil reaction, it will rotate in this way. So it will be clockwise direction. And the moment of base due to the moment of base at toy stripe. The moment of base acts at this way, so it will rotate in this way in clockwise direction. So maximum moment to point B, it will be equal to maximum moment, maximum moment of soil reaction, which is moment 1 minus moment of base, which is moment 2. So moment of base will be equal to moment 1, which is 39.7 minus 32229. So moment at base, it will be equal to 39.79 minus 3.29. It will be equal to 36.50. This is kilonewton per meter. Now, let's determine the area of reinforcement for the toy slab. Area of reinforcement is obtained by taking moment at base over 0.7 Fy weights. Now, it will be equal to maximum moment is 36.5 x.6 over 0.7 Fy, which is 500 times z. The value of z we take is for, because this z is obtained for the total base, so we use the value of the value of z is this one. Is similar for the hill slab, because both are the value of z for the base. So we multiply by 3 to 3. So the area of reinforcement for the toy slab will be equal to 6.5 x.6 divided by 0.87 times 500 times 3 to 3. It will be equal to 2x. This is millimeter square per meter. Now let's check for the minimum area. Minimum area it will be equal to 0.3 times 0.13 times width times h. But this h is equal to the thickness of what? Thickness of steam, which was 400 millimeter. So the area, the minimum weight will be equal to 0.001 times 1000 times h, which is 400. Minimum area, it will be equal to 5,000 millimeter square per meter. So because the area of toy slab is 260, this is less than the minimum area. Which is 520 millimeter square per meter. So the reinforcement will be because it is less than, the reinforcement will be required as for the minimum area, which is 5 millimeter square per meter. So this is area provided, which will provide for the minimum area. So to obtain the area required, for the minimum area, this minimum area is obtained at minimum area. For this case, it is no. Let's check for the diameter of 12. Diameter of 12, 5, 2. So the maximum area is this one. The maximum area beyond 520 millimeters square for the diameter of 12 is this one, 5. So we say it provides the high strength of 12 millimeter at a spacing of 12 millimeter center to center, which gives the area of 566 millimeter square per meter. This reinforcement for the toy provides at the bottom, because at the bottom. Because the soil pressure acts upward, so it provides the soil pressure it provides the reinforcement at the bottom. This is the final step for the determining the. Now we have obtained the reinforcement for the stem, the reinforcement as well as the reinforcement of the base. The next step is detailing of the reinforcement, detailing for the reinforcement of the cantilever. How can we detailing? This is cantilever was in this way. Cantilever, which have a heel slab and toe slab. Its reinforcement to be in this way. This cantilever. This cantilever should be provided with mesh reinforcement so to prevent seam cracking, to prevent shrinkage in seam cracking. So it will have the mesh reinforcement. This is mesh reinforcement. Mesh reinforcements. So to prevent shrinkage in seam cracking, as well as for the steam. It will be in this way. So, so for this inside the mesh reinforcement, there will be the number of bars. So the number of bars will be located in this way. With a spacing of 20 millimeter. With a spacing of 20 millimeter. 20 millimeter. With a spacing one bar after one another is 20 millimeters. As the reinforcement we have obtained in both steam and base. So this is steam wall. The steam wall we were obtaining the high strength of 20 millimeter at a spacing of 2 millimeter. This is at near face. And also we obtain H with diameter of 20 at a spacing of 2 millimeter at near face. At front, this is near face, this is front face. Near face, this is behind to the wall. This is front face. Front face is a face which is appear to the front face. This is near face behind the front face, which is acted to the soil. And this is a heel slab which provides the top H with a diameter of 20 millimeter, which provides at top face. At top face also provides the minimum at bottom face with a head with a diameter of 20 millimeter at a spacing of 12 millimeter at bottom face. At bottom face. Also, this system acts as distribution steel for both steam and base. So this toy provides a distribution steel. This distribution steel is distributing both top and bottom. This is distribution steel. Distribution steel, which gives the minimum area and provides the diameter of 20 millimeter at a spacing of 12 millimeters. So distribution steel with the high strings of 12 millimeter at a spacing of 200 millimeter, as well as for the base provides the distribution steel. The steel will distribute in both bottom and the top. So this is distribution steel. Distribution steel distribution steel with height strings of 12 at a spacing of 12 millimeter. So thank you for watching this video. Now we have designed from the first step up to the final step, which is detailing. If you found help in this video, please like and subscribe for more civil engineering tutorials. Thank you.